So within embedded, there's
Mhm.
kind of this conversion or this convergence with AI, and you kind of
Yeah,
alluded to it here, but the new buzzword that I'm sure we're going to be throwing around quite a bit on the podcast in the coming months and years is not agentic AI. We skipped right over that. Is now physical AI. And I think physical AI as electronics people is much more relevant than agentic, but I'm sure the physical AI will also be agentic. So maybe we'll use both buzzwords. So with physical AI, what kind of system architectures are possible with Samtec products? Because we've mentioned kind of a few different ways to construct the stack between your processor or your package and then the motherboard or multiple boards. So I'm interested to hear kind of from your perspective what's possible and what people are doing.
yeah, good question. I think this manifests itself in a few ways, and let me just talk each of those. Talk briefly about each of those ways. There is there is something we've been going to a lot of AI data shows over the last 5 to 7 years, like everybody else, and I think it was somebody from it's either Synopsys or Cadence. I can't remember who it was, but they started their question up. They started their question along the lines of, "Will AI design AI?" Right? Inferring that the EDA tools were going to become so intelligent that you could push a button and that would create the next AI accelerator, and then you could optimize the scale, the flow within the data center, and et cetera, et cetera.
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today, we're talking with Matt Burns, Director of Technical Marketing at Samtec. Previously, we had Scott McMorrow from Samtec on the show to discuss some aspects of signal integrity, and now I'm very happy to have someone else from Samtec come on the show and discuss some of Samtec's very cool products. Matt, thank you so much for being here today.
Hey Zach, great to be here, and welcome. Thank you for the nice introduction. Good to be here.
Yeah, absolutely. So you are a new guest on the show. Of course, when we have new guests, I always like to learn a little bit about their background. So if you could introduce yourself to our audience, tell us how you got into electronics.
Yeah, good thing. You know what? I wanted to get in electronics since I was a teenager, probably younger. As when I was 5, 6, 7 years old, I was always tearing apart our broken electronics. Alarm clocks, microwaves, whatever, because I was kind of curious to how they operated, and I saw these capacitors and resistors and basic microchips from the '80s. I'm old in those devices, and it sparked a curiosity about electronics. In high school, we started studying electronic theory, electromagnetic theory, especially in physics. I think it was my junior year in high school, and it just clicked. Ohm's law just clicked. I could see how electrons flowed in a circuit diagram, and I'm like, okay, I guess I'm the electrical engineer. Visit Penn State main campus in Central PA a couple months later, and that sealed my decision. Spent about 5 years. It took me about 5 years to get my BSE from Penn State, Maine, but I haven't looked back and have loved it ever since. Career-wise, designed for about 6 years, did apps engineering for about 5 years, and I've been in tech marketing for about in the interconnect industry probably for about the last 16 years. But so far so good. Loving every minute of it, and want to continue to leverage this ride as long as possible.
Yeah, I so identify with that, tearing open old electronics and, looking at
Mhm.
all the parts and wondering what everything does. And I think for me, my first kind of thing that created that itch to get more
Mhm.
curious and learn about electronics was I was in high school and we had like a computers class. I took all the
Mhm.
computers classes, and part of that was like you actually got to put together your own computer. I thought it was the coolest thing
Yeah.
ever.
Yeah, I got to give credit to my mom and dad too, because I did some dumb things when I was a kid. Like I realized that light bulbs could, were powered by electricity, but I took a DC bulb and put it on a 120-volt AC plug and then plugged it in and blew up my face. And thankfully the fuse box opened up and didn't start a fire. But when my dad heard that happen, I got an earful, and he's like, "Look, son, this is cool that you want to do this, but before you do anything like this, let me know." Again, so mom and dad were super cool with fostering that interest and moving it forward, but they were also patient with my brother and I because we kind of did dumb things, like I guess a lot of kids did when they're young, exploring their interests. But without that support, Zach, I don't know that I would have pursued the path, and here we are.
Yeah, yeah. Like I said, I so identify with that, and especially breaking some stuff sometimes.
Exactly.
One thing that's really interesting about Samtec is, you guys are pretty heavily involved in high speed interconnects, but I think for a lot of PCB designers, the connector is kind of an afterthought, and not even just the connector itself, but even like the trace routing entry into the connector. But there are so many products that rely on these high speed interconnects, and you can't just use any old off the shelf connector. They have to be actually intentionally designed for
Yeah.
the bandwidth or data rate you want. So as speeds have increased over time and digital data rates have increased, how have you seen connector products change?
Well, I think you hit on a key point in the design cycle where connectors are chosen, right? I remember early in my career, I'm designing telco devices, I'm designing medical devices, make the electronic circuit work, and figure out the connectors last. I mean, I remember specifically I was working at a CPAP manufacturer, and we had to make sure that the I/O expansion module worked. We picked the modem chipset, we picked the wireless chipset, we did all the things, and then we decided to pick the connector right before layout. And that turned out to be a 6-week process because we picked a connector that was too big and we had to, rejig it to get into the system. Samtec has this thought process left aligned. And what that basically means is the earlier, faster speeds go earlier and earlier in the design cycle, that connectors have to be thought about or chosen. And when you look at what's happening in the data center, when you look at what's going on with AI, which we'll talk about a little more in detail later, those connectors, interconnect, optical, copper, whatever, they have to be chosen at the same time as the semiconductor content. It's really it's a key part of the system architecture. So I think that's the biggest trend is that design paradigm of 10, 15, 20, 25 years ago, worrying about the connector at the end. In some instances, you still do that, right? Because not everybody's designing high tech, but interconnect is a part of the system. It's not an add-on. How have connectors changed? In general, smaller, faster, denser, right? I'm sure earlier in your career, all your connectors were 0.1 inch headers and sockets because they did everything, right? You could pass a few amps through them. You can get a couple megahertz through them, right? You could pass a signal acquisition system through it. Even RF to some frequency ranges. But
Still
now,
today, right? I mean,
yeah,
yeah.
and a lot of basic applications you can't because frankly, we sell a ton of that stuff still too. And by the way, thanks to all your listeners who continue to buy Samtec connectors. Sorry,
Right
that's my
here.
one plug. I apologize. that's my one. That's my one plug. I'm sorry, Zach.
No, it's fine.
But no, seriously, for advanced applications, you look at AI data center, you look at networking, you look at advanced compute, you look at test and measurement, right? There's other high precision fields, medical, some of the advanced medical devices that you see on the market. If you're not thinking about the interconnect earlier in the system, it's going to take longer, and you're dealing with connectors that are getting smaller and smaller, right? Our 0.1 inch, 2.54 millimeter. We're not the smallest connector vendor out there. We're not the densest because we don't play very well. We don't play well in handhelds like some of our competitors do, but we're still down to 0.5 millimeter pitch. That's freaking small. And not only is it a single pitch, but it's how do you break out dozens, hundreds, thousands of interconnects on a 0.5 millimeter pitch in a package. So, that's really the biggest challenge is it's continually evolving. You make small steps with anything else, similar to more, you think about Moore's law in the semiconductor area. We kind of have the analogous changes here in interconnect, but that's it. Smaller, faster, denser in a nutshell.
This is interesting too because you mentioned 0.5 millimeter pitch on connector pins, and I think I just got a good video idea about that, because typically when we talk about those kind of pitches, we're almost always referring to a BGA, right?
Mm-hmm.
Or maybe a connector, but it has like kind of the BGA pad array kind of footprint,
Exactly.
the kinds I'm talking about. Yeah, but
Yep.
that could actually be on the leads coming off of the connector. So it's not necessarily a leadless connector. You can actually see it coming off and branching off the sides.
Yeah, correct. And you look at a lot of the architectures that you see in some of these high performance systems, and that's exactly what it is, right? It doesn't necessarily have to be an interconnect. It could be an interposer, right? You're doing a die to a substrate to an interposer to a PCB, or just a substrate to a PCB. And you're at those pitches, right? Typically, you need to add the interconnect in some form or function in that architecture for ruggedization, for speed, for SI support, ease of manufacturing. But no, you're right. It goes back to what we were talking about earlier. Interconnect is a part of the architecture, and you need to consider how you break out those signals, tens, hundreds, thousands, from silicon to the system, and interconnect helps you do that throughout the architecture.
So I think this is a good segue because you mentioned packages and substrates, and one of the areas where connector performance has become pretty critical is not just in areas like PCIe and those kinds of high speeds, but now with 112G SerDes, 224G, 448. Of course, 112G has been commercialized, 224 being implemented, and 448, I think they finally figured out we're going to do PAM6 modulation on it. So pushing out the bandwidth a lot farther than what the PCB designers would like. But the connector products are just as important as, even attempting to get the signal into the PCB at 224 or 448. So give us an overview, if you could, of some of the connector products at these speeds and what they look like. And I bring this up because it really is a current topic, especially with AI and all this stuff being implemented in the data center.
Yeah. So let's look at AI and data center, because that's typically the application space. Networking, those are typically the application spaces that are driving the data rates that you and I are talking about. So let's start at 112. So for 112, that's really the first node that we start to see where, close to the package, on package interconnect is starting to become a reality. From Samtec's perspective, we have several, ASIC adjacent, or near chip solutions that we refer to. One family is our SciFly LP. It's a very low profile interconnect that's designed to go right next to the ASIC. It has a small profile. I think it's like 4.5 millimeter profile. It's low enough to fit underneath the heatsink on your system. We've seen customers implement that with, with conduction, liquid cooling, fan cooling, whatever, right? For those that are looking for maximum density at 112, ASIC adjacent, we have our Accelerate HP family. That's an open pin field array. I think we can get up to 400 pins in a connector. That's good both for near chip to cable, or if you have a mezzanine daughter card style application. We also have our Novray family. That's another mezzanine connector that's really optimized for crosstalk at those high speeds. 112 gigabit, you're talking about Nyquist at 32 gigahertz. We'll get to the higher Nyquist here in a second. And then on the front panel, you've got QSFP, QSF PDD. As data rates get faster, our thought process is, sorry, Zach, I know you're a PCB designer, get those signals out of the PCB into twin-X cable. Physics are what they are. Twin-X cable, 28 gauge, 34 gauge. It's about 1/4, 1/5 the loss of standard PCB materials. You can extend the signal reach over longer distances. So, from Samtec's world, we're moving mid-board, where the ASIC adjacent connectors are all the way up to the front panel or all the way up to the backplane. For 112 gigabit backplane, we've got our XMAX2 cable backplane infrastructure. So we use those copper twin-X cables not only inside the box but outside as well. Making that transition from 112 to 224. Again, smaller, faster, denser. What drives a lot of that system architecture, I think, is something like a Broadcom Tomahawk networking chip or a Marvell Terralinx networking chip. The latest solutions, 1024 differential pair on a single die, right? So how do you break that all out to the front panel of the backplane? Our solution is a substrate-based connector that we call SciFly HD. The substrate connector, 0.5 millimeter pitch. We have various flavors depending upon the transceiver count. 16 pair, 32 pair, 64 pair. We're looking at other solutions, 96 pair. The punchline with SciFly HD is I can put 16 of those connectors in a 95 millimeter by 95 millimeter package with the silicon die and have 102 terabit per second aggregate throughput on that package. We can route that copper to the front panel, using an OSFP cage, or we can route copper to the backplane using some of our 224 backplane interconnect. Or, because of all the infrastructure we see with AI, we can also change that pluggable connector from copper to optics. So SciFly HD gives us the same connector on the substrate, plug the copper in, take it out, put an optical transceiver on it, run optics to the front panel, run optics to the backplane for those applications, maybe GPU based, AI based, XPU based, where optical connectivity is a necessity. You mentioned 448. That we're like literally in preseason with 448. It's only been in the last 6 months where where we and our competitors have exhibited 448 capability over Interconnect. Typically, it's a surface mount or compression style connector using twin X cable. What sets Samtec apart is we're not using a compression connector there. It's just surface mount. I'm not sure that the encoding has been completely finalized, because I've seen some people talk about 448 PAM4, 448 PAM6. Obviously PAM6 in the 86 gigahertz region, PAM4 is in the 112 gigahertz region. But when you look at the 448 twin X solutions that we have, about a half meter long, we've got decent loss profiles over those solutions: 15 dB at 86 gigahertz, 20 dB at 112 gigahertz. So, while a lot of that is proof of concept and maybe a little demonstration platform right now, it's right around the corner. So, that's kind of a 3-minute overview of all of our 112, 224, 448 infrastructure. I don't know if I've ever done it that fast, Zach. So thanks for making me do that. I appreciate it. Obviously, we can go. Yeah, obviously we can go into more detail with any of your listeners offline for any of those solutions.
Yeah. And for folks that are interested in learning about some of these products, we'll include some links in the video description for folks that are watching on YouTube. So go ahead and check out some of those links, and you can see, I guess you can make some of these products a little more tangible.
Yep.
One thing that you had kind of mentioned in your high speed gloss over the available products and kind of how they function is something that has happened in server architecture, networking architecture as the speeds have gone up, which is the connectors have migrated away from the edge of the PCB and closer to the package. And so this has given us some new types of connectors. And I think there's near chip, and then there's co-packaged chip. So if you could, or not co-packaged chip, but co-packaged connector.
Co-packaged copper, near packaged copper, co-packaged optics, near packaged optics. Yeah, man, I've had, trust me, it's nuts trying to keep up with all the AI networking TLAs, but we'll get there eventually. So just the difference there. Because of density, because of the need to place the interconnect as close to the die as possible, co-packaged copper, co-packaged optics are reality. We've seen a little bit of that at 224. We're going to see a lot more of it at 448. And from our perspective, there's a lot of semantics in the industry, but in general, what we're seeing, co-packaged copper, co-packaged optics refers to some sort of electrical substrate-based connector attached to an HDI substrate with the system ASIC attached to that same substrate. There's typically a stiffener on there to make sure that the substrate stays coplanar, and then in that substrate-based socket, you have either a pluggable copper solution, which is purely passive copper, or you have a pluggable optical transceiver that uses the same electrical socket. So I'll make sure we get some links here for your listeners so that they can, and those on YouTube, so that they can see what we're talking about on the Samtec website. But that's what we're referencing. So you use an HDI substrate, the connector, the ASIC, the stiffener. Typically, you're working with an OSAT to create that subassembly, Zach. And that subassembly would come from the OSAT, go to the OEM, and then the OEM would attach that substrate-based solution to the final PCB. The benefit of that is optimized SI performance, because the trace length from the die to the connector is 10 millimeters, plus or minus. You can take the chip off, you can take the connector off the substrate, you eliminate the need for the substrate, and you can put a near package copper or near package optics electrical connector on the PCB, but the length from the die, the die transistors to the connectors maybe an inch and a half, depending upon how you lay out your system or the density of the connector. From in Samtec's world, we've noticed a 5 to 6 dB improvement using the co-packaged copper or co-packaged optics interconnect over the near packaged copper, near packaged interconnect. But there's trade-offs, right? The improved SI performance requires working with an OSAT. The system design is maybe a little bit more complex, maybe a little bit more expensive, but it gives you the SI performance that you need, which is essential at 224 and 448. The other thing that we're seeing too in the industry, and this is not necessarily a Samtec thing, but XPO as opposed to CPX. CPX is you're doing the O to E or the EDO conversion directly on the package. XPO is you're doing that out at the front panel. So there's a lot of system architectures. I'm trying to keep this straight while I'm talking about this, Zach. It's driving me crazy. But co-package interconnect is everywhere. In the last 4 weeks, I've been to DesignCon. We were at Embedded World. Last week was OFC. A lot of activity in the industry around multi-source MSAs, around CPX and XPO. So yeah, these things are reality. And frankly, what's driving it is our friends at NVIDIA. They're the not to mention anyone specifically. There's other AI chipset solutions out there or providers there, but they're the 800-pound gorilla in this industry. And the innovation that they're giving the industry, the competitors that they have, the Google TPUs, the AMD solutions, that's what's driving all this interconnect. The need to scale AI accelerators to handle these model sizes, and you're connecting everything copper at short range and optics at long range.
Yeah, so you mentioned something really important with the moving of the connectors from near chip to co-packaged, which is, you said, about a 5 to 6 dB improvement in total loss. So this would be essentially just because you've eliminated a via transition through the package, and instead you just kept all of the interconnect in package. And it's actually not just a via transition through the package. It's actually through the package, through the PCB, because it's usually strip line, and then back up another set of vias into the connector.
Exactly.
Yeah. So instead, keeping that all on package, you keep, a known good via structure at, smaller size, and then you just route a shorter distance over to the connector.
Yeah. And that's that reference I mentioned earlier, on the substrate or on the package, you're 10, 11 millimeters plus or minus. And then, if you're coming off the chip through the PCB to the connector, you're probably 25 to 30, millimeters or longer, depending upon how dense the system or how up the application is. So 1/3 the lens gives you that SI performance. And, when your total channel loss is, call it 30 to 35 dB, that 5 dB on the transmit, and that 5 dB on the receive path, that could be 1/3 your signal budget. So that, for system architectures, that's really hopefully that helps to illustrate and helps the listeners and your viewers understand the why co-packaged interconnect copper or optics is becoming so essential with these high speeds and with the density of transceivers that we see on current and next generation silicon.
Now, some of our folks in our audience and also folks that we've had on the show in the past are working in the Ultra HDI regime, where they're actually looking at like substrate-like PCBs, where basically the entire PCB is the substrate. Do you see that being practical with your data center customers, where they stop doing this kind of thing, where they have the chip and the substrate and then a separate PCB, and where they just do it all as one big assembly?
Interesting concept. I don't know that we've seen that at Samtec's perspective so far. We've seen some, without going to customer details, we've seen some things like that on the drawing boards. But, because I think the challenge, and this is just my initial response here, the amount of I/O that has to go in and out of the chip, the amount of I/O that has to go in and out of a 19-inch rack mount chassis, to me, you almost have to go substrate PCB chassis, unless you make the substrate 19 inches, 19 inches wide, and 1 unit high. That gets really expensive.
Right.
So I think in some applications it makes sense. I know there's some stuff going on in OCP that's kind of looking at wiring using twin X cabling as the entire system infrastructure. So you'd have maybe 2 or 3 or 4 substrates within the system, and then have sort of some substrate based solution. I haven't seen that at scale yet, personally. It may be out there more than I'm aware of, but it's definitely an alternative depending upon the application and depending upon the use case.
Yeah, I think one of the other issues with kind of those larger substrate like PCBs is probably warpage and misregistration, right? During the assembly process, if you're putting a bumped die onto that substrate, if there's any warpage or non-planarity, you create a huge problem with assembly defects, and now your yield starts to go down. And you don't really have that problem with the connector necessarily, right? It's only on the die.
Yeah, well, the analogy I would say there too is, with some of these systems I've talked about earlier about SciFly HD, we have to put a sifter down on something that's 100 millimeter by 100 millimeter, right, or 95 millimeter
right.
by 95 millimeter. So that's something that's like this big. You're building something that's it's too wide for the screen, but you get something that's 19-inch rack mount solution size. What you're saying about warpage, how much stiffener is you putting on it? How thick is that that substrate? How many layers? What's the cost? So for datacom style AI style rack infrastructure, I personally don't see how you do it at cost. But if you're doing something that's small, cable mount, maybe. I don't know. It's an interesting question. It's an interesting system architectural application. In some instances, I see how that could make sense, but personally, I don't see it in the data center or for AI scale up, scale out yet.
Well, time will tell, and I'm sure
Yeah.
some of our folks out there who are former guests and interested in this will be happy to come on and talk about it if
I'm
that
sure
ever does scale up.
Yeah.
So, kind of at the other end of the complexity spectrum, or maybe not less complex, just complex in different ways, is embedded systems. And you've seen some of that same miniaturization that we've been talking about with connector products also make its way into embedded devices, where you have more I/O, more features, more functions, more chips, on and on and on. So give us a good overview of what Samtec is doing to help designers that are building embedded systems, and especially high performance digital embedded systems.
No, great question. And, it's interesting that you bring this up, Zach, because I've had this conversation with a number of people. To me, I just mentioned earlier that, in the last 4 weeks, I've been at 2 data center centric trade shows with DesignCon and OFC. And then conversely, I was at an Embedded World in Germany a couple weeks ago, sandwiched between those two. And, the design node requirements couldn't be more opposite, right? OFC crowd, 448, DesignCon crowd, 448, Embedded World crowd, 3 to 5 years from now, 112, PCI 6, right? But here's the thing. This is something I think, and this has kind of crystallized my thinking on this at Samtec. Embedded solutions are getting faster and faster. I tend to think that they're a generation or two behind design center. So, 5 to 7 years, if you and I were having this conversation, would have the entire conversation around 112, right? Smaller PCBs, smaller connectors, lower loss materials, the fact that you're starting to introduce twin X cable, flyover type system architectures into the system. That design methodology we're starting to see in embedded, right?
Interesting. Why the lag?
Embedded doesn't need 448. Embedded doesn't need 224. Embedded doesn't need 112, right?
Well, that's fair, but maybe they need 56.
Well, and I guess that's where we're going with this. Is if you look at the roadmaps from the embedded chipset providers, 56, 112 is probably about the fastest I've seen so far. You look at some of the roadmaps for the FPGA suppliers, without mentioning them specifically. There's commercially available 112 right now. Yeah. There's roadmap for 224. That's probably not going to come out for another year or two, depending on who you ask and depending upon chipset skills. So the need to design 224 on an embedded controller for AI at the edge, not quite there yet. It'll probably be there in 2 to 4 years, but for now, it's like, how do I design for 112? And your point is right. If I'm an embedded engineer, 10 gigabit per second may be bleeding edge, right? And I have to get from 10 to 25. Or if I'm at 25 and you get from 25 to 56. The point I'm just trying to make is that the design iterations that the data center AI, networking communications folks went through 3 to 5 years ago, all that information is already available and you can make it available to the embedded ecosystem. It's just a matter of transferring it from one engineering community to another. So that's there. With that being said, what has Samtec done? Smaller, faster, denser, right? We're not designing 0.5 millimeter mezzanine connectors for embedded, but we are designing 0.635 millimeter, right? So our that interconnect node or that pitch, high density, open pin field, our Accelerate HD, our Accelerate HP families, those are ideal for next generation industry standards that need to get from PCI 3, PCI 4 to PCI 5, PCI 6, right? If you look at a PCI chem connector, it's a 1 millimeter spacing. You can get 128 gigabit out of that based on the SI suggestions or SI, the loss channel that PCI SIG provides for that interconnect. You can't get to 256 on that with PCI 8. At least we don't think so. That's a known signal channel that's been in use for 25 years. With embedded, those you don't have that same use case or that same signal channel. The signal channels are always changing, right? So the workhorse of embedded computing is ComExpress, right? ComExpress was the first introduced 20 years ago, right? So early 2000s, I think. My brain's a little fuzzy. Sorry. The connector that was designed for that when that came out, bleeding edge, it was supported PCI 3, I think, PCI 3.0. So that's 8 gigabit per second, 8 gigatrans per second. That spec has been optimized to get up to PCI 4, 16 gigabit per second. That connector can go faster. You're limited. So about 5 years ago, PicMig came out with the HPC Spec, completely different interconnect, that gives you the path to PCI 6. It's using our Accelerate HP connector. So smaller, faster, denser, open pin field array, smaller stack heights, 5 millimeter and 10 millimeter. And then, all the optimized signal breakout or breakout regions that we learned data center 5 to 10 years ago were given to the embedded community right now. So that's really what it is and then open standards, right? Because the embedded community loves open standards just as much as the data center guys, but the data center stuff changes every 2 years. In the embedded, it changes every 10 to 15 years. So we've really noticed over the last couple of years is how do we enable the embedded engineering ecosystem to operate at PCI 5, PCI 6 using the form factor of their choice to get the next generation of performance. And, from an industry standard standpoint, SCET OHFM, .C, the VITA90, VITA93 solutions, HPC 1.3, and there's others I'm forgetting. But all of those use high density, low profile mezzanines that operate up to PCI 5 or PCI 6. So that's kind of a long-winded answer, Zach, but again, it's providing that SI expertise either directly to the customers or through the industry standard bodies to enable the performance that you're talking about based on the chipsets that are available for embedded applications.
So within embedded, there's kind of this conversion or this convergence with AI, and you kind of alluded to it here, but the new buzzword that I'm sure we're going to be throwing around quite a bit on the podcast in the coming months and years is not agentic AI. We skipped right over that. Is now physical AI. And I think physical AI as electronics people is much more relevant than agentic, but I'm sure the physical AI will also be agentic. So maybe we'll use both buzzwords. So with physical AI, what kind of system architectures are possible with Samtec products? Because we've mentioned kind of a few different ways to construct the stack between your processor or your package and then the motherboard or multiple boards. So I'm interested to hear kind of from your perspective what's possible and what people are doing.
Yeah, good question. I think this manifests itself in a few ways, and let me just talk each of those. Talk briefly about each of those ways. There is there is something. We've been going to a lot of AI data shows over the last 5 to 7 years, like everybody else. And I think it was somebody from, it's either Synopsys or Cadence. I can't remember who it was, but they started their question up. They started their question along the lines of, will AI design AI, right? Inferring that the EDA tools were going to become so intelligent that, you could push a button and that would create the next AI accelerator. And then you could, optimize the scale, the flow within the data center, and et cetera, et cetera. We're not there yet. Obviously, the place and route and all the design challenges that go to creating a next gen ASIC are unique unto itself. And obviously AI is making the tools more intelligent to get things done more efficiently, et cetera, et cetera. So I think that's one manifestation. Physical AI to me, takes on many different infrastructure or many different form factors. And to me, physical AI at the edge, embedded computing, those all kind of complement each other. So I still think you're going to see physical AI using some of the more popular embedded computing industry standard form factors, HPC, this new OHFM, because every embedded chipset provider has some sort of AI algorithm or AI value add that they can put on their chipset, right? And that's true across FPGAs, ARM, x86, RISC-V, other open infrastructures, et cetera, et cetera. So I think you'll continue to see physical AI with existing form factors. I think the most interesting thing, and maybe this is just my opinion, but physical AI, the cross between physical AI and robotics, right? We're seeing humanoid robotics, it's just expanding like crazy, whether it's everything that Elon and his team's doing or a lot of the innovation that's coming out of China and APAC by extension. A lot of cool things that these humanoid robots can do. Sometimes I'm doom scrolling on LinkedIn late at night and it's crazy what I see, right? You see the same thing, right? So having the intelligence to be able to accomplish that requires unique form factors. And I'm not a specialist on humanoid robotic design, but those systems are evolving so quickly that eventually I think you'll start to see open source platforms there that leverage the AI capabilities and 5G, 6G capabilities for the wireless connectivity to control it as we go forward. So maybe that didn't answer your question specifically, Zach, but from my perspective, I think that's how we're going to see it. It's not going to be one physical manifestation. It's going to be, can we support the speeds? Can we support the throughput? Can we support the density? And can we come up with unique solutions that are needed based on the needs of the use case? And, Samtec celebrating our 50th anniversary here in 2026. We've been doing the same thing for 50 years. So whatever the industry throws at us, we're confident and we're committed and focused to coming up with something that works for whatever the use case is with physical AI or whatever comes up after that.
Yeah, I think with robotics, the form factors can get really interesting because the end goal is to make it not look like there's a giant computer mounted to the back
Exactly.
of this robot, right? So that's going to drive, making the stack smaller, which again, Samtec products, smaller, denser, faster, and then also being able to implement them on very odd shaped boards, depending on where this part of the system is being mounted. And I think that's the two areas where Samtec is going to excel.
Without question. And, we're excited about the opportunities that presents.
Awesome. Well, I think we're going to have to leave it there. If folks are interested in learning more about Samtec products, I encourage everyone to head over to YouTube. If you're not already there, take a look at the video description. We'll have a bunch of links here from Matt, and you can go learn about some Samtec products. Matt, thank you so much for being here with us today.
Thanks, Zach. Appreciate the time. Always a great conversation. We talk with you.
Absolutely. We'd love to have you back on in the future as you guys roll out more cool products for all the applications we've been talking about.
Anytime.
To everyone that's out there watching and listening, we've been talking with Matt Burns, a director of technical marketing at Samtec. If you're watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.